All right, hi everybody. So today I'm going to be talking about machine learning. I'm also going to be talking about how to do that a little bit with satellite data. These are both massive, massive, massive topics, so I'm going to apologize in advance for how much information this is. But just remember, there will be recordings, there are slides, there is a notebook. So how many of you have used machine learning before in your research? Yes, sure, yeah. That's actually a lot more than I expected. Keep your hands up. If you haven't used machine learning before, but you plan to or would like to at some point in the future use machine learning, raise your hands. Even more people. So that's most people in this room. So hopefully this will be a little bit helpful for you to provide some context on sort of the classes of algorithms, some different concepts that will be useful to you. If you haven't already, I strongly suggest you check out the Machine Learning Cloud Mask notebook because it sort of walks through how to do some of that in code. If you've already looked at that, this will provide you a little bit of a broader context, but we'll have a lot of the same concepts. So let's start off by talking about what machine learning is. Don't read all this text. What you need to know is it's a lot of different fields that all play in, that have all sort of led into this one sort of amalgam of different ideas that we call machine learning. It comes from linear algebra, which is kind of the language of machine learning. Signal processing is where a lot of the fundamental theory of information and entropy comes from. High-dimensional probability and statistics is super important when we're talking about these massive, highly parameterized models that live in these huge multidimensional spaces and trying to prove things about what happens to those models. Optimization is how we actually make these models good, how we make number go up. But probably the most important of all these, at least in my opinion, and the thing that, sort of the missing piece until the deep learning revolution was data and how we understand and process and think scientifically about data. So I think especially in earth science, you're going to find that you spend most of your time when you're working on machine learning actually just getting the data right. And if that last 10% is getting the machine learning to work, it'd be really helpful if we don't have to spend so much time working on that. We can really have some basic concepts, some high-level understanding of the APIs and tools we need to make machine learning work. So I'd like to divide this is usually what you'll see with the broad division of machine learning into 3 different categories. So we have supervised learning. This is probably what most of you think of when you think of machine learning, where we have some inputs, and we also know some labels, maybe labeled by humans, maybe by another satellite, usually by humans in the traditional context of machine learning. And we feed our inputs into a model. Our model makes predictions, which we compare with the correct answers. We grade that model, and then this red arrow is very important. We have a way to directly supervise the model on how wrong it was on that loss function. Unsupervised learning is when we don't have the right answer. We have a bunch of data, but we don't know where it belongs. So we have to find some method to sort of use the inherent structure of that data to tease out different classes or clusters within that data. Finally, you have reinforcement learning, which is probably the least relevant here for remote sensing, but it's still worth knowing about, in which we have an agent that exists within an environment. It sort of takes observations of that environment, decides on actions, and then it is rewarded. Now the key difference here between reinforcement learning and supervised learning, see that red arrow in the supervised learning? We can't really do that mathematically the same way in reinforcement learning, and so it gets its own category. So here's some example methods under each category. You've hopefully heard of some of these. In supervised learning, we have decision trees, random forests. You might have heard of SVM. Neural networks plus backpropagation, which is how we sort of train these neural networks, is what I'll spend most of my time talking about today. But it is very important to understand that these other methods exist. Sometimes you don't need an extremely you don't need a massive hammer for a tiny nail. And so you should use whatever is the simplest method that is effective. And for a lot of these other examples, there are one-liners in Python. There are packages like scikit-learn where you can extremely quickly get, for example, a random forest fitted on your data without really having to understand that much about how it actually works. Unsupervised learning, we have some other examples. A lot of you were saying PCA. We have k-means, which is a pretty simple but very effective algorithm, Gaussian mixture models. And then sort of below this green line, which is sort of dividing our non-deep learning from our deep learning approaches, we have self-supervised learning, where you sort of have the model use its own data and grade itself. It's a little bit complicated, but it's how a lot of these transformer models are pre-trained, if you've heard of that. Then reinforcement learning, we won't talk about any of those. There's some other variants to be aware of that are important. So we might have semi-supervised learning, where it's sort of a combination of supervised and unsupervised learning, where we might do some unsupervised and then some supervised, or vice versa. Transfer learning is Related but different, it's where we train a model on some data and then apply it or even fine-tune it on a different distribution of data. Finally, we have limited supervision, which is where we have supervised learning, but we have very little data, and so we have to figure out how to deal with that. So I'm going to go through a couple. Yep, go ahead, Pingwa. Yeah?
Why do you make a neural network plus backward propagation? Yeah.
Because that's what we're going to be talking about mostly today. Yeah. I'm just, because I think that's the thing that a lot of people might, yeah, it's evil, right? Might have a hard time understanding or might want a little bit more context for. So I'm going to go through some important distinctions about supervised learning. First is regression versus classification. On the left here, I had to get the directions right. We have a regression task where we need to actually fit a line to the data. Our line needs to sort of explain that data. Whereas classification, we're just trying to separate our data into different groups. Another important distinction is, and different, don't get these confused, is discriminative models versus generative models. So discriminative models only estimate the probability of your labels or your predictions, y, given the inputs, whereas your generative models model the joint distribution of both. This is very important. So your generative model is capable of generating new samples from your data distribution. That's because it's estimating the entire joint probability. Another common concept in machine learning and supervised learning is the idea of over and underfitting. So in the regression case, on the left here, we have a case of underfitting in which we have clearly quadratic data, but we've chosen a linear model which is incapable of capturing the primary form of variability in that data. Overfitting is where we let it be some super highly parameterized and jagged model, which gives us really, really low training error, but if we try to apply this to data it hasn't seen before, which is coming from this shape, it's more likely to be wrong. This middle one is just right. Same thing with classification. We can see here, especially in the classification case, overfitting it seems really bad because we end up with this totally over-engineered decision boundary that is not going to generalize. All right, so let's revisit this. I want to take this, and sorry, but I'm going to add some math, just a little bit, just to help us understand the rest of these slides. So we'll call our inputs x. We'll call our model a function f that operates on x. Our outputs will be y hat, so that's our predictions, right? The right answer, our labels, our targets, are just y, and then our loss function is this fancy L. We'll come back to that. But they're on the axis labels for now. So here's an example, thank you, Patrick, of regressing chlorophyll A. So you see we have our model over time. It fits to this curve. Another example in practice is trying to classify phytoplankton types. So we're using k nearest neighbors here. So this is actually a supervised. Don't mix this up with k-means. This is supervised. We have training data where we know which classes they fit into, and then we get a new data point, and we take the nearest neighbor, and we see that its nearest neighbor is in the Prochlorococcus group, and so we assign it to that class. But now let's talk about neural networks. So I think this word is scary to a lot of people, but these are actually very, very simple once you understand them. So this is sort of the simplest kind of neural network, which is called a multi-layer perceptron. So the way that MLPs work is they have fully connected, they fully connect each layer with a subsequent layer. So to add some math, let's look at, we have our inputs coming in on the bottom here, these x's. So think of x as some vector. Then we multiply each x with a bunch of weights. And that fully connects to each output after the first hidden layer. We also optionally add a bias term. So we can write this either as a sum, right? So y sub I equals the sum of the weights times our features plus this bias term. And we do that for each y or each y in this layer. Or we can write it with matrix vector notation, which is just a lot more compact and nicer, where it's just the multiplication of our weight matrix by our input vector plus some bias vector. So when we add more layers, it's the same thing, right? So we can think of, OK, well, let's write out, instead of O, we'll use H to represent the outputs at some hidden layer. Let's add another layer now. So we see H2 is just our second weight matrix times the output from the first layer plus another bias term. But now we have a problem. This is a pretty big problem, which is actually, if we multiply this all out, we end up with this term times x plus this vector. And we realized that we've actually accidentally flattened our layers, and our two fully connected linear layers, into one bigger fully connected linear layer. This is still linear. No matter how many of these we add together, it's always going to be linear. We're never, ever going to be able to model any nonlinear behavior, which is a big problem. So how do we fix this? We add activation functions. So what we do is we separate each one of our layers by some nonlinear function. And it turns out that by doing this, we magically get this wonderful property called universal function approximation, which means that as we make our network wider and deeper, we can arbitrarily approximate, to an arbitrary tolerance, any function. There's proofs for this. Historically, activation functions, we used to use what was called sigmoid. We still use it in some cases, but we used to use this as like the activation function for like every layer, which causes problems, basically because the difference in these tails is so small that it actually causes numerical issues. Your numbers get really, really small, and you don't get very good updates. Now we use something much simpler for most of the time, or variants of this, which is called ReLU, or rectified linear unit, which is just flat until it hits 0, and then it's just the identity function. And this is enough. Turns out, somehow miraculously, just by adding this one little weird hinge after every layer, now we have these extremely powerful universal function approximators. So how do we train these? Well, we have to have some loss functions. We have to have some way of comparing our predictions and our outputs. And we have to do so in a way that is differentiable. We'll talk more about that soon. These are sometimes the same thing as our evaluation metrics, the way that we sort of decide how good our model is at the end of the day. But sometimes they're not, because sometimes our evaluation metrics aren't differentiable. And so then we need to have something that is differentiable that approximates our goals, basically. This is also sometimes called the objective function, because it's our objective. So for example, in regression, we might use mean squared error, which is often our evaluation metric, and it's differentiable. So it's fine. We just take the mean squared error between our predictions and our output, our predictions and our targets. In classification, we use something called cross-entropy loss, which is sort of a way of measuring the difference between two probability distributions, the amount of information that is sort of overlapping between our predictions and our targets. So back to this graph. This MLP. So let's think about all these connections here between our inputs and our first hidden layer and our outputs as weight matrices. This first one will be 3 by 4, and this next one will be 4 by 2, right? So let's talk about what we can do with this loss function. So now that we've computed our loss on our outputs after we propagate forward through our network, what's cool is because this is differentiable, we can take the derivative of it. We can use the chain rule to take the derivative of the loss function with respect to anything in our entire computation graph. We can say, OK, I want to know this connection right here, which is W, our first weight matrix at, say, W1, 2, right? So we want this connection here. We can take this, this derivative very easily just by chaining these derivatives together. So there's sort of after the forward pass, there's the backward pass that goes back through our network and propagates our loss values and basically blames each parameter. How wrong am I because of you? So now that we have this loss, what's called the gradient for each parameter, we can take an update. We can update each parameter to make our loss lower. This is called gradient descent. So imagine we pick two of these at random, and we might graph them and find a loss landscape that is very hilly like this. Gradient descent will just go downhill, and our hope is that eventually it gets to some sort of minimum, whether it's a global or local minimum. Now, obviously, this is happening in a much higher dimensional space. For this, it'd be happening in 12 plus 8, so like a 20-dimensional space for this tiny neural network, which you can't visualize. But this is good intuition anyways. It might kind of look like this. So the way that we do this, we don't just take a giant step. We take small steps. And this is determined by what's called our step size, also known as our learning rate. So this is a very important parameter that sort of controls the dynamics of how our optimization will go. If we pick a learning rate or a step size that is too high, we're going to end up overshooting the minimum. If we pick one that's too low, it's going to take us forever to get there. So gradient descent basically means that we go through all of our training data, we compute the gradient with respect to that, and then take an update. But that's really slow, because iterating through all of our data might actually be take a really long time if we have a lot of data. So there's this other idea called stochastic gradient descent. What we do is we chunk up our data into little, what are called batches, and We go through, and each time we go through a batch, we take a step just with the gradient with respect to that batch. And so what that means is our updates are a little bit more random or more stochastic, but it ends up being a whole lot more effective in practice. Now, it is very important to note that stochastic gradient descent in practice is almost certainly not what you will be using. There are much better variants, but they all operate on similar principles. They're all gradient-based methods. The one that is a very good starting point, what I use in most of my work, because it works, is just atom. So you don't need to understand how it works. It works similarly to this with a bunch of very complex optimization theory, but that's an important note. So let's talk a little bit more about evaluation metrics. If I didn't add this before, feel free to interrupt anytime with questions also, if you have anything to ask. So I made a distinction before between loss functions and evaluation metrics. So evaluation metrics are really our final test of how well we did. They're what we care about. We want our loss function to resemble our evaluation metrics as much as possible. Sometimes they're the same, sometimes they're not. But let's go through some evaluation metrics. So in classification, we might care about, so on the left you have what's called a receiver operating curve, or receiver operating characteristic curve, which most people don't even know that acronym, just call it ROC curves. And the idea is that we want the area under this graph of our false positive rate versus our true positive rate to be as big as possible. If we are perfect, we would have a perfect right angle here. That's one way of thinking about it. There's a similar but more complicated alternative for image classification that is called mean average precision. I won't get into that now. Then we can also just think about things in terms of our true positives or false positives and come up with metrics based on that. There's a lot of loss or evaluation metrics, and in like the instance segmentation or semantic segmentation, basically where we're masking data, like in the notebook, that use metrics like this. Regression is a lot simpler. We can just use like mean absolute error or mean squared error depending on what we care about. And these are differentiable, so these can just be our loss functions too. So I mentioned earlier what batches are. They're like chunks of our data, and we take a step for each batch. We divide it up. An instance is just one line of data. So a batch will have many instances. It's a bundle of instances. And so our batch size, how many instances in each batch, is very important. Usually the bigger the better, but asterisk. Basically, the batch size controls the stochasticity of our updates and sort of the convergence speed. Epochs, or one epoch or multiple epochs, refers to how many times we've gone through our entire data set. So this also, how many epochs you need varies greatly based on how big your data is and what your problem is and how big your model is. Early stopping is another useful concept, which is basically like if you get to a point where you're doing good enough and you don't want to keep training, you can cut it off. I talked about going through your whole data set, but usually you don't want to go through your whole data set. You want to cut it up into a few different pieces. You want to have a training set, a validation set, and a test set. It is important to understand that in machine learning, validation means a very different thing than it does in earth science and remote sensing, so don't mix them up. Training is the data that you use to train your parameters, to fit your parameters. Now, what are your parameters? They're the numbers that go into your model. So the weight matrix, the bias, those are parameters. Validation is sort of what you use to optimize your hyperparameters. So what are your hyperparameters? Well, how many layers are in my network? How wide are they? What what optimizer am I using? What step size am I using? What's my batch size? So you keep a validation set so that you can make smart decisions, and you can say, oh, when I repeated this experiment with a different network architecture or a different optimizer, I got better results. Testing, you don't optimize anything with this. You hold this out until you are done, and that is your way of proving, hey, my method is good, the choices I made are great, and it generalizes without me like overfitting my, my model design to this data. Let's go through a really quick example. This is not actual code. It's pretty close, but it is not actual code. There's similar code in the notebook that I recommend you go through, but just to sort of give you an idea of the flow of this. At first, you would do some setup. You would initialize a model, your optimizer, your loss function, and then you would iterate through your epochs. So maybe you want to run for 10 epochs or 100 or 1,000. For each epoch, then you go through batches in your trained data. Now these are these are going to be shuffled, so they're going to be different every time. You take predictions with respect to your model. You get your loss function between your predictions and your targets. Then you zero out the gradients of your optimizer. This is kind of PyTorch style code, but different libraries have different ways of doing this. Then you do that backwards pass. So where pred equals model, that's your forward pass. Loss.backward, it's built in. It'll automatically do everything backwards for you. And then your optimizer takes a step. It updates your model. And then after you've done that for all of your training data, you might every so often report some validation metrics. You might not do this every epoch, or maybe you do. You go through your validation set and you'll say, how well are we doing? How are we doing on data that we haven't explicitly trained on? So let's revisit this idea of over and underfitting now that we have nice curves that show us our training and validation losses. Underfitting, well, the issue is actually not that these are close to each other. The issue is that they're not that low, right? So you can see that in the optimal case, our training loss actually gets a lot lower. So maybe here our model doesn't have a high enough capacity, or it hasn't trained for long enough. If we're overfitting, well, that's because our model is just memorizing the training set, and then when you ask it about the validation data, it's applying its logic that only works on the training set, and it's not working. So you might want to regularize your data a little bit more or get more data. In the middle, we have our perfect case, our sweet spot, where you don't want this distance to be big, but usually there is a little bit of a gap, and that's OK. But you want it to be as close as possible, and you don't want this massive gap, and you want them both to go down to a reasonable loss function. And sort of what that means, what a reasonable loss is something you kind of will get a sense for with practice, but it's also why we have evaluation metrics, because sometimes these numbers don't directly map onto what we care about. Yeah, go ahead.
Can you go back just
Yep.
before you leave this?
Yeah.
So, using this kind of gradient descent models in other contexts, we will select our stopping point based on the slope
Yes.
of the red and
Right.
the blue,
Well, it'd be based on the slope.
or the red, or
Well,
whatever.
well, yeah. So that's actually the thing is you can use the blue. You can say, well, my validation loss isn't going down anymore, so I'm going to stop. That's the point of having a validation set as opposed to a test set, right? Because one of your hyperparameters is how long did I train it for,
Yeah.
and your validation set you can optimize your hyperparameters with respect to that. So you can say once my validation loss stops going down, maybe you have a situation where your validation loss stops going down, but your training loss is still going down, and after that you're just going to be overfitting. And you don't want to do that. So you really actually should stop. You should do early stopping when your validation loss plateaus, and not when your training loss plateaus.
So like in this one here on the far right,
Right. You would have wanted to stop like here.
you want to stop there, but
Or
it
here,
looks
yeah.
as if you had stopped there before the validation starts going south.
Yep.
The red line would still be decreasing a lot.
Yeah, you're overfitting anyways in this case. I mean, this is also a made-up graph, right? Like this might not reflect super accurately onto real data. But yeah, early stopping is good, but if you have, it might not solve all overfitting. I mean, it's not really a solution to overfitting, right? It's a way of stopping overfitting from happening if you get to a point in training where after that you might have overfitting, but if you're going to overfit from the start, it's not going to fix that. Does that make sense?
Yeah, it's okay. We can talk about this. On
Yeah,
the drive back.
sure. There's lots of papers about this too. Every single slide I've talked about, there's like 1,000 papers about every single one. Yeah, go ahead.
So the middle one is a good fit.
Mm-hmm.
Is there any objective criteria for the right?
No, not really. I mean, that's kind of what's hard about this, right? Is there's a lot of different ways you can think about it. I mean, you don't want your validation loss to start going up. And if it stops going down, then there's not really a point anymore. Your validation loss is your way of informing your decisions. You're not supposed to peak at your testing loss yet.
So if
Yeah.
you have a data set,
Mm-hmm.
you divide it into two types. One is clean, one is validation.
I would say 3, because you have a held out test set, which is like your final set.
Eventually, we have the ability to generate more data. How can I tell when should I stop?
Oh, when you should stop generating more data?
Yeah, I could
If it's like an expensive.
Use small data.
Yeah. No, that's hard, and I think it's something you have to. I mean, there's not like a short answer to that question, right? Like, you might have a trade-off between how expensive it is to generate more data and how the diminishing your returns you're getting for your model's accuracy as you're adding more and more data. And this is a thing we have to think very carefully about when we're collecting data sets. When we're especially, it takes a lot of human hours and money to label these very large data sets, and like at a certain point, it probably stops being worth it at a certain size.
Think about neural network fast
Right.
backward propagation, like a supervised retrieval, that if we generate like some random number of cases based on the model, and then we use that to train neural network, and we do all the things we could do, divide them into three groups, one for training, one for validation, one for testing.
Right.
All that runs through. Is there any reasons for us to doubt we should generate more data to test?
Yeah. So, I mean, that's what's listed here in the overfitting section, right? One of the things it says is get more data. So if you're overfitting, you might just not have enough data. There's a relationship between how many parameters are in your model and how much data you need to train it. There's also a relationship between how many parameters in your model and how complex the actual relationship between your inputs and outputs is. So say you have some really complex problem, it's very hard. There's the relationship between your inputs and outputs is highly nonlinear, and you would actually need a very deep network to be able to capture that relationship. You're also going to need a lot of data to train that network. Whereas if there's a much simpler relationship where maybe like a 2-layer network with not that many parameters is enough to capture that relationship, you won't need as much data. But there's not like a set in stone answer to, when it stops being worth it to collect more data. Yeah. So one thing I haven't mentioned so far is how we actually do this numerically. So one of the things that has made deep learning a lot more possible in the modern era is graphics processing units. So you guys, for pretty much everything you've been doing, unless you've been using my machine learning tutorial or something like that, you've been doing everything on your CPUs, which are very good for more complex operations. They give you a lot more flexibility on what kind of operations you're doing. But GPUs are really, really good at very large matrix operations. So if you just need to multiply a bunch of numbers together really, really fast, these are way faster than your CPUs will be. And there are libraries to do this for general purpose computing rather than just games or graphics. And that's where CUDA comes in. So you would probably use something, you'd write high-level code in Python and use something like PyTorch or any of these other machine learning libraries that will interface with CUDA. CUDA is a language that lets you talk to your NVIDIA graphics card and give it instructions so that you don't have to write really difficult to write, complex, low-level graphics code, and you can write your nice little Python, NumPy-like operations, and it'll get compiled and run on the graphics card and be super, super fast. So this is how this actually works in practice, because everything I've shown is matrix vector operations.
So, like, I hear people say GPUs are better than CPUs, but, like, I don't really understand why. Is it parallel computing, like what
Right.
Ian was talking about in Dask, or, like, what's kind of behind the...
They're not better than CPUs, right? Like they are capable of, they're more restricted in some ways. So they're less capable of more flexible instruction types. And if you need a lot of like intercommunication between your data, like if GPUs have a harder time with that. But if you have if you're doing highly parallel stuff, where you just really most of what you're doing is just big giant matrix vector operations, GPUs are going to be amazing because they're meant for graphics, and that's all that graphics is at a low level. At a low level is like lots of geometry, lots of drawing to the screen, really big matrices. GPUs awesome for that. Blow CPUs out of the water, like.
And would be better than, like, Dask?
It depends on what you're doing, because a lot of stuff that you would be able to do with Dask and that like Ian was talking about would be either extremely difficult or even potentially impossible to do on GPUs. So they're more restricted, but if you can get your stuff to run on GPU, it will probably be the fastest. Yeah, go ahead.
Just a quick comment. I mean, a typical GPU might have 10,000 cores.
Yeah.
And so you're actually running, I mean, in the same way Dask does parallel work.
Yep.
You might get a 5,000 or 8,000, even 10,000 times speed up.
Yeah.
Because it's managing that distribution.
You might, if you're curious about this, you might take the machine learning cloud mass tutorial and then not actually care about any of the machine learning part and just use it as a way to learn how you can do NumPy-like operations on a GPU. Turns out in Python and PyTorch, it's as simple as just adding .CUDA, really, to your objects, and then it moves them to a GPU, and then doing operations there. And I encourage you to play around with that and see what it does to your speed. Now, I will say, timing code that uses the GPU, that uses CUDA, that uses the GPU, is like using timeit is not going to work. And if you're curious about that, we can talk more about it later. But it's kind of beyond the scope of this. Right. So now let's talk about satellite imagery. Finally, so this, we have this really important property that is actually more true in satellite imagery than it is in ground level imagery, which is we have spatial context and translational symmetry. Translational symmetry especially, right? So, if I have a cloud in the top left of this image, also thank you for the beautiful image. Karina made this. It's wonderful. It's from our First Light stuff, and I can't stop looking at it. But if these clouds in the top left of the image, well, the logic that's going to help you recognize that that's a cloud is not going to be that different from the logic in the bottom right of the image. In fact, it should probably be the same, right? Clouds are going to look like clouds regardless of where they are. However, if we just turn this image into a giant vector and then pass it into a fully connected neural network, the network is going to have to relearn how to recognize clouds at every single pixel. Alternatively, you could just pass in one pixel at a time, like have each instance be a single pixel, but then it doesn't have any spatial context. And spatial context might be really important. Say I'm looking for clouds over an icy region. Well, it might be good to know that I'm over an icy region, and so I should be a little bit more careful about just thinking that something is a cloud because it's bright. So the spatial context is super important. Translational symmetry is sort of something you should be thinking about when you're thinking about image processing. I want to a lot of you probably are very familiar with the idea of convolution, but I just want to go back over it real quick. You can take two signals and you can convolve them. This is one-dimensional continuous convolution here, and you can see that we take these two signals, f and g, and we flip this g right here, and we sort of sliding window multiply them, and this is our output signal, right? Pretty simple. Input's two signals, output is another signal. We can think about convolution in 2 dimensions in a very similar way. So what we're going to have is instead of these, we have 2-dimensional signals now. We have an input and an output. But, well, sorry, we have an input and a kernel. This kernel, we're going to use a 3x3 one here. It's filled with these, right? We're going to slide it over our input. We're going to multiply all the overlaps and then add it up over the 3x3. And then that gives us one output. And we're going to slide it over and do that again here. And we're going to do it over and over. And eventually, it's going to fill this whole image with the multiplication, the element-wise multiplications of this and the kernel. Note, we didn't flip the kernel here. This is actually cross-correlation, and it's called convolution anyways. It's fine. So, well, what does this do? Well, actually, the specific kernel I showed you over here, notice how it has a 5 in the middle and -1s around the 5. This is a sharpening filter. So if we apply it to this image, it's a little hard to see unless you kind of squint, but this image on the right is actually a lot sharper than the image on the left, and all we did was convolve it with this 3x3 kernel. And it did this really crazy thing and changes the appearance of our image. So we can think about meaningful image operations in terms of kernels that are applied to images. You can do blurs like this, you can find edges, you can do all sorts of powerful stuff with these really tiny kernels. So there's a little bit of a caveat here is the previous example, what we did is we applied this independently to each color channel, but the convolution we're going to talk about is actually going to operate simultaneously on all the channels in an image. So typically in like ground level imagery, we have RGB image cubes, but in something like OCI, this dimension is a lot bigger. So it's important to understand the difference between these two things. You have to remember that a lot of the best practices in computer vision have been developed for these kinds of images and not for these kinds of images. So you might have to be really careful about just taking off-the-shelf models and applying it to stuff like OCI because it can cause problems. So you have to think more carefully about this. You have to think outside of the box and be cautious about this. But so it's important to remember that there is this channel dimension. So convolution is actually, in our context, is going to be sort of a linear combination of all the channels of input. So you can kind of think of convolution as being fully connected, like our multi-layer perceptron was, in the channel dimensions, but as a sliding window in the spatial dimensions. These graphics are really great. There's the website that these are from, these animations are from, is linked at the end. I strongly recommend you check it out if you have any confusions about how convolution works, because it's an amazing, I'm very visual, and this really helps me understand how they work. So a little bit more details. Convolutional layers, they're going to work very similar to our fully connected layers, but they also have a bias. They're going to have activation functions because they're still linear, and so they need a nonlinearity. And they're still differentiable, so we can still backpropagate through them. The number of parameters you'll have in a convolutional layer is your kernel size. I'm assuming it's the same width and height. Call it k squared times your number of input channels times your number of output channels plus your number of output channels if you have a bias. And you'll note that this does not depend on the image size. Another detail, convolutional layers, you might include padding, so we add maybe zeros around the edges of our image so that the output is the same size as the input. But not always. If we don't add this padding, then actually every time we apply a convolutional layer, it's going to shrink the input a little bit, depending on how big our kernel is. Another concept to think about and to keep in mind when you think about convolutional neural networks is the idea of a receptive field. So I've gone back to one dimension here. This is a one-dimensional convolution over some input. And you'll notice that at this output location here, if we go back through these three wide convolutions over 3 layers, this output can actually be affected by all these inputs. And so that's the receptive field of this output. So this is something to think about when you design these networks. Classification networks are designed to have a receptive field that is actually much, much bigger than the image size so that you can have a spatial context that spans your entire input image. Let's go through this interactive demo because I think it gives you it's just really cool and is a great, a great way to visualize this. So this is, in real time, it's going to show you the intermediate outputs after each layer of a partially convolutional and then at the end partially fully connected network. This is trained on MNIST, which is a data set of hand-drawn digits. So I'm going to draw a very simple but not very good 5. And you can see, so after the first layer, these are the intermediate features. And you can actually mouse over and see where they're connected. Then we're applying what's called a max pooling, which is kind of just like taking the max over some window and kind of crunching our features into smaller sizes. Then we have another convolutional layer, and you can see how each pixel depends on stuff in the inputs, right? Another max pooling layer. And then finally, this is all fed into a couple fully connected layers at the end. And you can see it's very small, but all the way at the top, we have the confidences in each class. And it has correctly identified that this is a 5. That's kind of cool. Yeah.
So is it always better the more layers you have?
No, no. Yeah, so that's a really good question, right? So the question is, is it always better the more layers you have? Well, no. It depends on how hard the task is, and it depends on how much data you have. So if I was to approach something like MNIST here, which frankly is a solved problem, has been a solved problem for a very long time. This is easy. This is actually a tiny network, right? This is not a very advanced network, and it does a fairly good job on this. If I was to add just a ridiculous amount of layers, if I was going to use something like a modern transformer architecture and train it on this, it would just be totally overkill. It would probably overfit, and I would have issues. There wouldn't be enough data to train it, right? So there's this coupling between how much data you have, how parameterized your model should be, like how many parameters it should have, and how long it takes to train, and how hard the task is.
Follow-up.
Yeah.
But if it's seeing like more information, I guess in my head, it kind of makes me feel like it would be more likely to smooth rather than like overfit.
Well, so think about it this way. If I have a bunch of pages to write down how to, like, I don't know, say I'm like translating a sentence, right? If I have 1 million pages to write down how to translate a sentence, I can just memorize every sentence in my training data. If I only have 10 pages, I have to think a lot more carefully about what I write down in terms of how I understand language. And that 10-page guide is probably more likely to generalize to new sentences I haven't seen before, whereas that 1 million-page thing is just rewriting the original data in a new way, is not going to work on a brand new sentence, if that makes sense. It's a little bit of a weird example, but the over-parameterized models will memorize the training sets, and they'll do perfectly on that. because they have the capacity to. That's the easiest path to success, right? Instead of having to, come up with more compact representations of what's actually happening.
So in this model, like how many parameters are being shipped?
That's a good question.
That first layer is what, 6?
Yeah.
6 represents 6.
Yeah. So let's, I don't actually know what the, this doesn't have a full explanation of what the convolutional layers are. And I would have to sit here and count pixels. I think it's probably a 3x3 convolution, but let's assume it is just for the purposes of this. So we have some big, I think these are 64 by 64 images, maybe 32. No, they're 32 by 32. We're going to pass them. We have some convolutional layer that is probably 3x3, and it's going from 1 channel to 6 channels. So 1 times 6 times 3 times 3. Bias is a little bit more complicated. It's just going to add 3 times 3. So let's write it down. Do I have a marker up here? Maybe not. Well, in the case of no bias, it's 1 times 6 times 3 times 3. That easy. You just multiply your input channels, output channels, and then your kernel size squared.
And so
That's for the first layer.
so is that just going to one of these images or to go to the end of the layer?
So 6 is because this is generating 6 different images. You can really think of these as a cube in practice. This is separating them out so you can kind of visualize them, which is kind of fun. But yeah. So this is, like I said, this is a very small network. This has, that's actually the biggest layers are going to be these dense layers at the end. Because since they're fully connected, they have kind of big weight matrices. So probably this second to last dense layer, which is going from this one long vector to this other one, is going to be just the size of the inputs times the size of the outputs. And that's going to be the biggest layer. But still, this network has at most like a few thousand parameters, which is really small. Like modern architectures, like transform architectures, have like billions of parameters. Yeah. Oh, sorry. Mm-hmm.
Do people think about adding I don't know as a solution?
That's a really, really good question, right? So one thing that's hard, and there's a lot of work on, but is a difficult area, is like understanding uncertainty, like thinking about variance and uncertainty with these networks. So actually, here, what the network is doing is it's outputting a confidence for each of the classes. So let's start over. Let's clear my drawing and let's draw this. So you're going to see the output. It's not really sure what this is. There's a little bit of, it might think it's a 0. It probably thinks it's a 7, I guess. But it's a little bit more uncertain. So that's a little bit of one measure that you might use in the structures. Like it's not. Yes, that's one way of doing it. But you'll note that that is different from giving you an actual variance. Like that is not the same thing. And it is important to understand that unless you explicitly bake in variance to how you design your architecture and how you're optimizing it, it is not going to give you that. You can read about Bayesian neural networks if you're curious. Oh.
I'd like to ask a question about resolution.
Sure.
Which may not be true for this case. And for the input output, do they have the same spatial resolution?
Right. So normally when you, so remember when I showed you the padding where you can add padding around? So that, if you have a 3x3 kernel and you apply it to an image, it's going to chop off the border. Because it's this, every time you put the center of that 3x3, say, over the top left of your image, it won't have enough input. It'll be sort of hanging over the edge. So you can't actually put it all the way to the top left. You have to go over one by one. And so to fit it there, you have to chop off that one by one boundary. Say you had a 7x7 kernel instead, which nobody does anymore, but say you did, you would chop off 3 pixels. So that's one way in which it changes your image resolution. So you have to think carefully about what are actually the sizes of my tensor as it passes through my network, my intermediate features, right? There's other things that change the size of that too. So here, there's something I haven't explained, which is max pooling. I think it's max pooling. It might also be average pooling. But what it's doing is this is actually taking, I believe, 2x2 windows in each of the inputs. Yeah, see, it's hard to tell, but if I mouse over a pixel, it's actually selecting a 2x2 little window, and it's taking the max in that window. So this also changes the resolution. So there's...
Is that true that
No. Depends on how you set up your network. So you can actually do what's called like transpose convolutions, where you increase the resolution. There's a lot of tricks to convolution that I haven't explained, like stride, dilation. There's ways to do what's called transpose convolution, of where you actually upsample your network. So if you read about like UNet, for example, it's very commonly used in remote sensing. What it has is two branches, one that downsamples your features, and then it takes those downsample features and upsamples them again, and then it has these little skip connections between. So it combines the simpler features at higher spatial resolutions with the more complex features at lower spatial resolutions, and turns that all back into one. So you can be very creative with how you change the sizes of your image as it passes through. For classification, you usually want to collapse down to one. I mean, traditionally, you collapse down to one value because you only have one output, which is what classes this whole image. But for something like cloud masking, I sort of very lazily design the network in the cloud masking tutorial to always pad by one in every layer so that the shape stays the same, and that works. Yeah.
There will be some tests, especially for the lens and color classification case study. We feel like after training this model and apply the model to the new imagery, the output resolutions very much lower than the input.
Yeah. Oh, the number of like labels you have? I guess I'm not really sure what the relationship is. We should talk after so I can understand more of what your data is, because yeah, I'm not sure I fully understand. Yeah.
So just a curiosity, is there a reason for those performing the convolution only the spatial domain, or they are neural networks that work on the full domain?
That's a great question. Yeah.
I've never seen it.
It exists, actually. So that's a really good question. The question is why do we only convolve over the spatial dimensions? Well, we don't. Sometimes we convolve over other dimensions. So there's actually 3D convolutions. So they might operate on volumetric features. The reason that we don't do that often is because those are really slow. Yeah, well, they produce, yeah. So first of all, they're bigger because they add a whole another dimension. So all your features are now bigger. All your weight vec matrices are now bigger, but also your intermediate features are going to be bigger. So that's one reason. So one common thing you'll see is like separable convolutions, where you have a two-dimensional convolution and then a one-dimensional convolution in succession, rather than having a full 3D convolution, because that ends up working about as well, but is way faster. But yeah, you might think about combining these things, about convolving over other dimensions. I will add also, so the channel dimension, you don't usually convolve over because it doesn't have translational symmetry in the same way that your image dimensions do. So like, let's think about OCI. There might, the way that spectral features behave in the UV is not going to be the same as they behave in the infrared. Any other questions? I'm starting to run out of time, so let's, how do I do this view? Zoom out? No. There we go. Sorry. Back to this. I'll briefly talk about data augmentation. Sometimes you can get more data for free. It turns out that if you're trying to look for clouds, then those clouds probably look the same if they're upside down or rotated or whatever in your images. So this, you can just freely add a bunch of data by applying some of these transformations, and it will help your network to be invariant to those transformations, and just makes it generalize better. But I think this is maybe the most important part of this talk is that, as I hinted earlier, convolutional networks are not designed for satellite data, at least not most papers, right? Like the history of it is mostly designed around ground level imagery. We operate especially at earth science scale, we operate at a huge, huge scale. So while spatial context is important, it might not always be that important. You might not need to look hundreds of kilometers away to understand what phytoplankton is doing at this location. It's also not multi-scale in the same way. In ground level imagery, we have perspective variations of scale, right? Like you look way bigger to me than she does, right? That doesn't happen with satellite data, or at least very little, right? Like there's very little perspective variation in size. Also, our number of channels, like I said before, totally different. So if you're doubling your channel size every layer, like is common in convolutional architectures, but you start with 286 channels from OCI, you're going to end up with way, way too big of your features. So you have to be careful about this stuff. Yeah, finally, just check these resources out if you want to see where I got the figures from and get more resources. Any other questions?
Is there any special, because you said this neural network not designed for separate data, is there anything we should pay attention to?
Yeah. I mean, there are, well, so those are some. Yeah, be careful about channel depth if you're dealing with something like OCI. We had this issue, right? So we have a paper, well, a preprint currently that is where we used a UNet on polder data, so it's multi-angle, and we also include geometric features. So our channel dimension is huge because we just stack it into an image cube. So we couldn't use the same channel, like feature depth scheme as most UNet papers do because we were running out of VRAM. So we had to think a little bit more carefully about slowly ramping that up in like a log scale instead, and that ended up working better. But so that's one pitfall. But there's lots. I mean, there's also a lot of papers about doing computer vision in satellite imagery, but the main line of progress on a lot of these techniques is not at all considering our particular needs, especially not in earth science.
Does data augmentation works for ocean color? Because I've seen it for geometry of like forestation, for example, but in ocean coloring, you get
It depends on what you're doing, right? So if you're just trying to predict like, yeah, I guess it depends on what you're predicting. So I was showing it with cloud masking, and there it makes sense. I'd have to think more carefully about like what, if you're just trying to predict ocean color, I don't know. Yeah, like.
I think it would matter for physics, like the spin of the Earth, right, is going to have different, like V
Yeah.
velocities are different than Z velocities, which ultimately affects like the shape, like the patch.
Yeah, one thing to consider is one common way of doing data augmentation that I didn't show is just adding noise to your data, and that's one way of regularizing kind of, and there's other ways of doing that. But that might not be a terrible idea. You have to be really careful about how you do it, I'm sure, but that's one thought. I don't know. But it'd be a really interesting paper. Right? Any other questions? Cool. Thanks, everybody.